record this session. Okay, guys. Okay, so what is the question 5 that you said, Alan, of the homework?
The population of Canada in 2033.
Okay, just give me a second. So that is question 5 of the homework. So it says that the population in 2007 was 33 million. Okay.
The population is growing at a rate of 2.2. Why equation represents the population?
Okay. Growth rate is equal to 2.2% per year. Okay.
Why equation population?
Mm-hmm. Okay. Okay, so we want to find a formula that represent or present the population in terms of the time t in years, okay? And the initial time, so we have here to assume that the initial time is 2007. And the initial population is 33 million. So in general, so the exponential growth, so the mathematical models for exponential growth is like, so here I use P for population. So say P of T is equal to P0 and then e to the power KT. That is the general exponential growth model, okay? And P0 is the initial population. So here what we know is that the growth rate is 2.2% per year. So that means it is 2.2. Is it 2.2 or 22? Is it 2.2 over 100? Which is equal to, if it's 2.2 over 100, it's just equal to 0.22. Okay, so by this information, we know that P of T plus 1 is equal to P of T plus 0.022 P of T. Does it make sense? So after 1 year, you get this. Which is, so now the right-hand side, so the right-hand side is equal to, let me just rewrite this. The P of T plus 1 is equal to, so the right-hand side is just 1.022 of P of T. Okay. Now, if you plug this into the population model, then on the left-hand side, you get P0 times e to the power k times t plus 1. On the right hand side, you get 1.022 e to the power kt. And of course, p0. I forgot p0. Now the p0 and p0 are gone. And then if you divide the two sides by e to the kt, so you get e to the power k times t plus 1 divided by e to the power kt is equal to 1.0. So here, what you get, it follows that e to the power k is equal to 1.022, okay? Right?
Mhm.
Because e to the power kt, on the top you have kt plus k, e to the power kt plus k. And then if you subtract the kt, you get e to the power k. Do you know what I mean?
Mm.
So this is basically, this guy is just e to the power k. Okay, so e to the power k is 1.022. Okay, so we got it. So we have the model, exact model for the population. So because this is the model. So PT is P0 e to the power KT. But I know that e to the power K is this guy. So if I plug it here, is equal to P0 e to the power K to the power T. And this is equal to P0, then e to the power K is 1.022, then to the power T. So we have PT, and we know that the P0, the initial population, is 33 million. So what the question wants? Or just, does the question only want to write the model?
Yeah.
That's it.
And then numbers say was the approximate population in 2020.
Okay, in 2020. So the initial year is 2007. So if the initial year is 2007, that's the t equal to 0. So the initial year is 2007. So that means in 2020 or 2022.
2020.
So what is t in 2020?
3. Almost 13.
13.
Plug in.
You just plug in.
We'll get approximate.
So P of 2020 is equal to exactly P of 13, which is equal to 33 times 1.022 to the power 13 in terms of million. So here there is a lesson that we can learn from this. The lesson is, it is true that in general, the general model for the exponential growth is like this model. But once you have the k, the value of k, then you can just simplify this and we can just write it as this model, P0 1.022 to the power t. And here you see that how to find this k. So that means the bottom line is whenever you know that the growth rate is like, say, 2%, imagine it's just 2%, then the model would be pt is equal to p0 times 1.02 to the power t. Okay. Okay. Is that clear?
Mhm.
Does anyone have a question?
How to prove question 19. I didn't prove the identity.
Okay. What is question 19?
Log base n log base n times over log base n times.
So
Proven
what is the left hand side? Log.
base n
What is the base? M or N?
n
N.
Yeah.
Okay.
log n
This.
now base is n. Both of the base. No, I'm sorry.
Oh, okay. I got it. Log x, you mean this?
Yeah.
And here is
n
N. Here is M, right? Okay. So let's try. I mean, there are different ways, but let's try. So imagine that, how to do this? Okay. I think I have some idea. Okay, so imagine that I want to prove this identity. Imagine that log of x with base n is equal to y. Okay, so that means what? That means x is equal to n to the power y, right? Okay. Now let's plug this into the original. Just look at the right-hand side of this equation. So I want to work on the right-hand side. So log x with base n over log x with base m is equal to, but we know that log x with base n is y over log of, but x is n to the power y. So it's, I just write n to the power y, and here is m. So you have y over, but this guy, the denominator is just y times log of n with base m. Right? So you get is equal to 1 over log of n with base m. And this is equal to what?
Log M base N.
Log m with base m.
Oh.
I mean, there, yeah. Okay.
Okay.
Okay, so what we learned in this during the last 2 weeks, so we saw logarithm and exponential. And so you learned 2 new functions. One is the exponential function, I would say. So let's try, like, say 2 to the power x or e to the power x. Okay. And what is, if y is equal to e to the power x, then we know that the inverse of this function is logarithm. So then x is equal to, but the inverse, the logarithm with base e, we usually denote it by ln. That is the natural logarithm. So x is equal to ln of y. Okay, so that means the inverse of the e to the power x, which I denote by f inverse of x, is just ln of x. And we saw that the graph of these 2 functions, how it looks like the graph. So you basically have these 2 shapes. One is e to the power x, is going like this. And the other one is ln of x. Okay. Okay, so we have these 2 important functions which are inverse of each other's. And what is the domain of, so another thing, just to summarize. So first of all, the domain of ln, or the domain of any logarithm, is the set of positive numbers. So you see from here, the picture. So for ln or logarithm, any logarithm, the domain is just positive numbers. Okay. If you have f of x equal to log x, or f of x equal to ln of x, the domain of f is just positive numbers. So that means, for example, if I give you this function, f of x is equal to 3x plus 2 divided by 1 minus 2x. And I ask you, oh, sorry, and you have ln. F of x is equal to ln of this guy. And I ask you, find the domain. Find the domain. So what you need to do, then we know that the domain of ln is positive. So that means 3x plus 2 over 1 minus 2x has to be positive. Now you have to solve this inequality. The same thing that we have done before. You remember that you need to make a table, right?
It has rooted at 0. All the result must be positive.
Okay, so you have a table, you put the roots. So this is the x. What is the root of the numerator? 3x plus 2 is minus 2 over 3. What is the root of the denominator? 1 half. 1 over 2. So you have two expressions. The top is 3x plus 2. And then you have 1 minus 2x. And then you have the whole thing. 3x plus 2 over. No, it cannot have, it cannot be 0. So 3x plus 2 is 0 when x is minus 2 over 3. And here is positive, here is negative. 1 minus 2x is 0 when x equal to 1 half. But when x is greater than 1 half, this is negative. When x is less than 1 half, it's positive. And 3x plus 2 over 1 minus 2x is 0 when x is minus 2 over 3. It's not defined, does not exist when x equal to 1 half. It's positive here, negative here, negative. So the domain that we are looking for is this region. That means the domain x has to be greater than minus 2 over 3 and less than 1. Okay. So that's the domain of log. Another thing you should know is that the function e to the x, so f of x equal to e to the x, or f of x equal to 10 to the x, or 2 to the x, it doesn't matter. They have a horizontal asymptote. What is the horizontal asymptote of these guys? Y equal to 0. Because when x goes to infinity, minus infinity, then f of x goes to 0. And you remember the graph of these guys. And this is the horizontal asymptote. You see here is the horizontal asymptote. So y is equal to 0 is a horizontal asymptote for e to the x or 10 to the x. But you can also have e to the negative x. So e to the negative x is like this. So f of x equal to e to the negative x. Again, what is the horizontal asymptote? Y equal to 0. But this time, when x goes to positive infinity, then f of x goes to 0. For e to the negative x. You basically switch negative and positive, right? I mean that the fact behind this is that e to the power negative infinity is 0. Or 2 to the power negative infinity is 0. If you have a number that is greater than 1, like the number e, or like 2 or 10, and you take the power negative infinity, then you get 0. Okay. Now, what is the range of e to the x? Or 10 to the x? What is the range of e to the x? I mean, look at this picture. What is the range of this function?
From 0 to infinite.
And it doesn't include 0.
Yes.
So open interval 0 to infinity is the range of it. How about range of e to the negative x? E to the negative x. I mean, this is e to the negative x. And this one is e to the x. What is the range of e to the negative x?
I think it's the same.
It's the same. Because just you flip the shape, the range doesn't change. Okay. Now, if I ask you, what is the range of function, like what is the range of f of x equal to e to the x minus 10? What is the range of this guy? E to the x minus 10. Then what is the horizontal asymptote of this function?
Negative 10.
Negative 10, right. So you have this, imagine that this is negative 10. So it's something like this. So the range, you just transform the range. So the range now, I mean, you just transform the graph, right?
Mm-hmm.
You have a vertical transformation downward, right? So the range would be what?
Open interval from negative 10 to infinite.
Yeah. What is the range of log or ln? What is the range of ln or log?
Real number.
Every real number, the set of all real numbers. Because log is something like this. And it goes forever.
Mm-hmm.
So the range of this one is all real numbers. So range of if f of x is log x or ln of x, I mean. So the range of this guy range of f is just all real numbers. Okay, guys?
Mm-hmm.
Okay, now let me give you, tell you something about the inverse in general. So I tell you that if y, and this is like a very important thing, is y is equal to like a to the power x, that's equivalent to saying that x equal to log y with base a. Okay. So that means if you imagine that so if f of x is a to the power x, right? So f inverse of x f inverse of x is log x with base a. So let's look more carefully what we have done. If you have a function like f of x equal to a to the x, or you can say y is equal to a to the x. In order to find the inverse, what you need to do is to find x in terms of y, and then you are done. Because if y, for example, here, if y is equal to a to the x, that we know that x equal to log y with base a, then you switch the name of x and y, and then that basically gives you the inverse function. Okay, let me give you another example. So in general, if you have if you have y equal to f of x, that means x equal to f inverse of y. Okay. And the picture, I mean, if you want to have a picture in your mind, it's very, I mean, it could be challenging, but you just have to think about it. So this is just a picture. So imagine that this is x, this is f, and this is y, which is equal to f of x. Then that means x equal to f inverse of y. So y equal to f of x, and then x is equal to f inverse of y. So in general, that means that's the guiding principle. If you have a function f of x, if you want to find the inverse, just try to find x in terms of y. Okay. Example, very easy example. So y is equal to 2x plus 1. Find the inverse, or say that f of x is equal to 2x plus 1. So in order to find the inverse, so you just write y is equal to 2x plus 1, and you try to find x as in terms of y. Just solve for x. So what you have here, so 2x is equal to y minus 1, right? That means x is 1/2 of y minus 1. So x is equal to 1/2 of y minus 1/2. That's it. Because here now you can say that inverse of this function, f inverse, is equal to 1/2 x minus 1/2. You just change so you just, whenever, so you here you get x equal to 1/2 y minus 1/2. You just replace y with x, then this gives you the inverse function. Okay, so that was an easy example. Let's do some more complicated example. Example 2. So say that f of x equal to 1 minus x over 2x plus 1. I want you to find the inverse. Can someone tell me the inverse? So you know how to start, how to begin. That's the most important thing. How you begin? You just write y is equal to 1 minus x over 2x plus 1, and you try to solve for x. Do you know how to proceed from here? So you just have to you can multiply y by 2x minus 2x plus 1, and this is equal to 1 minus x. So that means 2xy plus y is equal to 1 minus x. You take y to the right hand side and you take x to the left hand side. You have 2xy plus x equal to 1 minus y. Now you can factor x, you can factor out x, you get x times 2y plus 1 is equal to 1 minus y. And then you have x. Right?
Mhm.
Okay, so you have x equal to 1 minus y divided by 2y plus 1. So that means, having said that, that means f inverse is what? Now, if you want to answer the question, what is f inverse?
F inverse equal y minus 1 to y plus 1.
No, but in terms of x, f inverse of x is 1 minus x over 2x plus 1.
Yes.
Okay. Okay, guys?
Mhm.
And just to recall some of the rules or identities, some laws of logarithm. So first you see that log x plus log y is equal to log of xy. And again, I want to emphasize that here the base doesn't matter. So the base can be here, the base is 10. We usually, when you don't put anything, that means the base is 10. But some writers, when you don't put anything for log, they assume that the base is e. So, I mean, it's sometimes, I know it's confusing, but when you don't put anything, it's either 10 or e. That means natural logarithm. So for some people, logarithm is just natural logarithm. So the most important logarithm is natural logarithm, and that's true. So ln is the logarithm. So all other logarithm can be obtained from natural logarithms. Okay. Anyway, so here I just want to emphasize the base doesn't matter. So this law holds for any base. And the second law is that log of x minus log y is equal to log of x divided by y. 3 minus log x is equal to log of 1 over x. 4 r times log x, or maybe it's better to say log x to the r. And 5 log of b with base a is equal to log of b with base c divided by log of a with base c, and this is equal to, we can use natural logarithm, ln of b divided by ln of a. That means if you let c be equal to a, if the base is e, then you will get the natural logarithm, ln. Okay. And that's pretty much it. So another thing that we just saw, we used today is that, maybe that's the 6th. 1 over log of a with base b is log. Of course, here you should be careful about x and y and the domain, because here there are some conditions. X and y, for instance, has to be positive. And when you say log b with base a, that means b first have to be positive, then a again is a positive as not equal to 1. So you have to be careful about the restrictions of log. I mean, you cannot say log of 3 with base minus 2. This doesn't make sense. The base cannot be minus 2. Or you cannot say log of minus 4. Minus 4 cannot be in the domain of log. I mean, is not in the domain of log.
Can be negative.
Okay. Okay, guys. So what we have learned during the last weeks, you got to know logarithm and exponential functions. And you knew that and you know that these are inverse of each other. And in general, you know the concept of inverse of a function. I mean, I didn't talk much about it, but that's also important concept. So you have a function f with some domain, so if say that is A is in the domain of f, and this is B, so if B is equal to f of A, then you can say that A is equal to f inverse of B. But in order to have inverse, a function has to be one-to-one. That means if you have another thing like A prime, and A prime also goes to B, then this function cannot have inverse. Because if you want to say what is the inverse of, what is f inverse of B, you have two options, A or A prime. So a function that is not one-to-one doesn't have inverse. But if a function is one-to-one, that means for any element in the range, there is only one element in the domain that corresponds to that. Then you can have inverse. So one-to-one functions. But maybe I will talk about these properties, general properties or characteristics of function in another unit. We will see this. But since we talked about inverse function, it's important to know that only one-to-one functions have inverse, like e to the power x or a to the power x, exponential. It's one-to-one. So it has inverse.